Hey everyone, and welcome. Today I'm going to do a divide and conquer algorithm called merge sort. So, sorting large amounts of information is a task that many people who deal with computers are just going to have to do on a daily basis. The problem is that sorting can take a long time. Let's take a bubble sort for example. Even if we only have 100,000 or so numbers, which isn't a lot by any means, it already takes over a minute to complete. Sure, a minute doesn't seem like that long. Honestly, we can all wait a minute while it sorts. But if we have 200,000, 500,000, a million, or even 2 million numbers, the time it takes for a bubble sort to actually sort those numbers increases exponentially. This is where the power of divide and conquer algorithms come into play. And with merge sort, we'll just see why they're super useful while comparing it to a bubble sort, something that we all learned in CSC 150 or 250. So what is a divide and conquer algorithm? Well, they're really a family of algorithms that, instead of just trying to do a problem right away, it divides up the problem into smaller and smaller sections, conquering each smaller section instead of just tackling the biggest problem all at once. It then combines these smaller conquered sections into the final solution. This is usually done through recursion, breaking up a process in half until it's the smallest it can possibly be, and then working its way back up to the full problem one step at a time. By breaking down a problem like this into its smaller pieces, it's actually much faster way of computating things rather than trying to do everything all at once. And today we'll be doing that with the merge sort. We'll be learning what a merge sort is, how it works, why it works, the bigO of it, and several examples of merge sort working. So merge sort's name kind of give away exactly what it does. It sorts lists and then merges them together, continuing to sort and merge until the entire list is sorted. And here's just a quick demonstration of how a merge sort works. So I'm just going to create a list of 4 numbers. Let's just say it's like 3, 9, 7, 2. So the first step of merge sort is making the list the smallest it possibly can be by dividing the list in half. So that's the first step. We divide the list in half. So this half, instead of being one list of 4 elements, we have 2 lists of 2 elements. This still isn't the smallest possible it can be though. We can have a list of 1 element. So we'll just do that again. We'll break each list in half one more time. So then we got 3, 9, 7, 2. All right. As you can see, these are the smallest elements possible. We can't break down a single number any further. So this is where we actually start sorting. We merge them, and now we're going to sort them. So we only compare adjacent lists with one another. So that means we're only going to compare this 3 with this 9 for the first step. So let's do that. So we know 3 is smaller than 9, so it goes in the list like that. 3 and then 9. And then the same thing happens here. We just compare this second half, the adjacent lists with one another. 7 and 2. So we know 2 is smaller than 7, so 2 gets sorted first, and then 7. And then finally, we do it again, because we're not back to the original problem. So this is the really cool thing about merge sorting though. We know that this 9 over here is going to get sorted after this 3. That's because we already sorted the 9, and we already know that 9 is bigger than 3. So we don't have to worry about it until that 3 gets sorted. Same thing over here. We only have to worry about this 7 over here once we sort this 2. Again, that's because it's already sorted. We don't need to sort something that we already sorted. So let's do this. So let's actually sort this list. So we compare the 3 and the 2 first. Well, we know 2 is smaller than 3, so 2 gets first. I'm just going to cross it out just so we can visualize it being marked. So then we compare the 3 and the 7. Well, we know 3 is smaller than 7, so we can place the 3 down. Notice I didn't compare the 3 with the 2 again because we already know it's sorted. So then we do the same thing again. 7. We compare the 9 and the 7. So we know the 7 is smaller than 9, so we place down the 7, and then 9's the last one. And there we go. We have the sorted list. So let's do a slightly more complicated one. Maybe not the full example, but 4, 5, 6, 1, 2, 3, 4, 5, 6, 7, 8. So I'm just going to write down random numbers: 7, 2, 8, 9, 1, 6, 4, 3. Again, let's break down the list in half again. So we have 4 here and 4 here, so it gets broken in half. So we go 7, 2, 8, 9. And then 1, 6, 4, 3 over here. And we break it in half again. 7, 2, 8, 9. Then 1, 6, 4, 3. And one more time, because it's not the smallest element. So we go 7, 2, 8, 9, 1, 6, 4, 3. Perfect. And now we'll do what we did when there's only 4 numbers. Compare adjacent lists. So we compare the 7 and the 2. Well, we know 2 is smaller than 7, so we just do that. And then we compare the 8 and the 9. We know 8 is smaller than 9, so it goes like that again. We compare the 1 and 6. We know 1 is smaller than 6. And lastly, we compare the 4 and the 3. We know 3 is smaller than 4. Then we do it again. So remember, we're only working with halves. So that means we're only going to do these 2 and then these 2. We're not doing the full list just yet. So let's just divide that line in half, just so it's more clear. So let's do this. So 2 and 8. We know 2 is smaller than 8, and then we put 2 down, and then we basically mark off the 2. Then we do 7 and 8. Well, hey, we know 7 is smaller than 8, so we can mark it off in 2. And look at that. The list is already sorted. Just to put 8 and 9, because we already know these 2 are sorted from this step up here. So we don't have to sort them again. Let's do the same thing over here. There we go. So 1 and 3. We know 1 is smaller than 3, so we can put it down and basically mark it off. 6 and 3. We know 3 is smaller than 6, so we can basically cross it off and put it down. 6 and 4. Again, 4 is smaller, and then finally 6. Almost done. And we do this list one more time. And this is going to be the final step, and we'll have the original list sorted. So let's just line this up. So we should have 8 cells. So 1, 2, 3, 4, 5, 6, 7, 8. So then we compare the 2 and the 1. We know 1 is smaller, so we do that, mark it off. We compare the 2 and the 3. No, 2 is smaller than 3, so we mark off 2 and copy it down. 7 and 3. We know 3 is smaller than 7, mark it off, put it down. 7 and 4. Hey, we know 4 is smaller, so we can put 4 down, mark it off. 7 and 6. Again, 6 is smaller, put it down, cross it off. And look at that. This is already sorted. We already know that it's sorted. So we can just put down 7, 8, 9, and hey, we got the list sorted. You know, from 7 to 8, 9, 1, 6, 4, 3, to 1, 2, 3, 4, 6, 7, 8, 9. Alright. But why is merge? So now that we've seen merge sort done, just how exactly does it work, right? It's super efficient, as we can see. We're not comparing every number with every other number, so it's much faster than a bubble sort. But after all, we can have a sorted list in O of 1 if we just say the list is already sorted and don't actually look at it. So how do we know that this is always going to sort the list? It's because what you've seen of by breaking it down into smaller and smaller pieces, we only have to worry about one number at a time. We only have to worry about the adjacent list at a time without having to worry about every single possible way that the list can be sorted. This is just so much faster computationally wise and just saves so much unnecessary checking, basically. Compare this to like a bubble sort. We all know bubble sort. We all love bubble sort. It's, again, one of the first algorithms of sorting that we've learned in college, maybe even before college. But it has to compare every number essentially with every other number. You can do a few little optimizations here, checking if it's swapped, not worrying about the last number, things like that. But it's still going to have to do a lot more checks than a merge sort. And just to show you about that, let's talk about bigO. Now, we're all higher level computer science students, but just as a quick review so we all know what bigO is, bigO is essentially just an upper bound of an approximate estimation. I know that's a lot of, unsure words. Upper bound of an estimation, that's just a completely random number, right? Well, not really. See, it gives us a super useful way of just letting us know at a glance which algorithm, on average, is going to be better and more useful than another one. And again, I'm going to show you why merge sorts bigO is much better than bubble sort and why that is. So let's calculate the bigO of bubble sort. So no matter what, we're going to have to go through a list one at a time. We're always going to have to go through a list at least once. This makes sure that it's actually sorted. So no matter what, the bigO of any sorting algorithm is going to be bigger than O of n. So let's see what a bubble sort does. Well, a bubble sort goes through a list twice, right? It goes through any list twice. So that means it's going to have O of n times n. One n for the first time it goes through the list, and a second n for the second time it goes through the list. This means it's O of n squared. See that exponential? That means anytime we add a number, it's going to have a much greater impact than people might initially assume. If we double the amount of numbers of items in a list we have, we don't just double the time, we actually quadruple the time it'll take to actually sort them all. But what about merge sort? How do we see the bigO of merge sort? Well, there's 3 steps to a merge sort. There's the divide step, in which we divide the lists in half. There's the merge step. And then there's the sort step. I think those two should be reversed, but overall it doesn't matter. Those are the 3 essential steps we're going to have to do. So first, the divide step. The divide step, we're breaking down the list in half recursively until its smallest element. This means it's going to be O of log n. So yeah, that's the first step. With merge and sort, they are both actually going to have O of n. This is because, as you can see above here, we only go through the list one time when sorting them. We don't go through it twice, and they're also essentially done at the same step. So both of them only have O of n. So we combine them into O of n log n. And just, again, reminder of bigO, this log is actually log base 2 of n. This is just because, we're in computer world, we're dealing with binary. That's why. But that's all and good. But it's personally, I think, a little bit confusing on exactly why merge sort is useful without seeing some examples, right? I'm telling you it's better than bubble sort. I'm telling you that O of n log n is better than O of n squared. I'm telling you it's better than that, but exactly how much better? Well, I ran a lot of tests. This is how I spent my Friday and Saturday of spring break. I ran a lot of tests. And so we started with a random bubble sort. So I first sorted, excuse me. So I first sorted 10,000 numbers randomly sorting bubble sort. So, and you can see here that you can't really see the numbers. That's because even though bubble sort is super inefficient, 10,000 just isn't a lot. It took an average about 530 milliseconds to run. With, again, super easy. We all can wait that time. However, even just 10x increasing the numbers, like I said in bigO, it didn't double the time, but it didn't 10x the time, but actually 100x the time. So that means our 100k run of our random bubble sort took 52 seconds about, almost 100 times longer than the 10k. I didn't stop there. I also did 1 million. And as you can see, each run took well over an hour and 20 minutes. The average for each run took an average of 1 hour, 24 minutes, 28 seconds, and 355 milliseconds. That's such an insanely long time. I have much better things to do than just stare at my computer for that long. And I run this test 5 times. I just created a quick script and done it while I was sleeping. I didn't stop there. 2 million. I only did this test once, and I hope you can see why. The one time I did this test, it took 5 hours, 37 minutes, 3 seconds, and 434 milliseconds. Again, such an insane amount of time. Doubling the amount of numbers we took, about 4x how many things we have. And I'll show you the code of that I use for bubble sorting in a little bit. So I also wanted to give bubble sort the best chance it is. See, bubble sort is really only bad when it's not its best case scenario. So I decided to give it its best case scenario. I did the exact same amount of numbers, 10k, 100k, 1 million, 2 million, but made sure the numbers were already in order. So on average, the 10k already sorted was 0.021 seconds. 100k was about 0.1318 seconds. 1 million that was already sorted was 1.2514 seconds. Excuse me. And then finally, the 2 million was 2.4268 seconds. Again, this is the best time because I'm going to show you later that merge sort is almost always going to be the best, but not technically always. I couldn't just leave it at that. I had to do bubble sort's worst case scenario as well to make sure I'm really showing you all why merge sort compares and why it's better. So again, 10k, you can barely see it, took an average of 627 milliseconds. 100k took about 1 minute and 407 milliseconds. Again, didn't stop there. 1 million took an average of 1 hour, 35 minutes, 38 seconds, 566 milliseconds. And then finally, 2 million. Bubble sort's worst case scenario took 6 hours, 23 minutes, 27 seconds, and 301 milliseconds. Again, did this while I was asleep Saturday night, recording this Sunday. Alright, so now that we know what bubble sort did, let's see what merge sort was able to do. Much better. You can immediately see how much better. just right off the bat. So on average, a merge sort for the random numbers, for 10,000, it took 0.025 milliseconds. 100,000 took 0.186 milliseconds. 1 million took 1 second, 808 milliseconds. And 2 million took 3 seconds and 666 milliseconds. That is much better for 2 million than the 5 hours, 37 minutes, 3 seconds, 434 milliseconds it took for the same random data when compared to a bubble sort. But here's something that's strange. You see, merge sort isn't always the best. 10K, it took an average of 0.0242 seconds. 100K took an average of 0.1692 seconds. 1 million took an average of 1.6426 seconds. And 2 million took an average of 3.2208 seconds. That's very similar to what it took with its random data, and I'll tell you why in just a second. It's also slower than the bubble sort. You see, let's just compare 2 million. So the 2 million bubble sort took an average of 2.4268 milliseconds, while it took merge sort an average of 3.2208 milliseconds. Again, I'll get to exactly why that is in a little bit, but just keep that in mind. If a list is already sorted or practically, or like only 1 or 2 items less, maybe a merge sort isn't the best sorting mechanism. But as you can see with the reverse, with the data in the backwards order, usually it's going to be better. So again, the 10,000 took 0.022 seconds. 100,000 took 0.170 seconds. 1 million took 1 second, 656 milliseconds. And 2 million took 3 seconds, 317 milliseconds. That's very similar to the other steps it took. So you can see as you can see, they're all pretty close together in their timings, despite, having already sorted data, random data, and reverse data. So this is for one really main reason. You see, the bubble sort algorithm that I wrote checks if a number is swapped or not. And if it finds that no numbers were swapped, we know that the list is sorted. That means it can end early. As you can see with the merge sort, we're going to do one more example of a merge sort. Just 4 numbers, 1, 2, 3, 4. So a bubble sort would check 1. 1 is smaller than 2, it would check 2, 2 is smaller than 3, check 3, 3 is smaller than 4, and that's the end of the list. So bubble sort wouldn't have to do anything, and it's done. Merge sort, on the other hand, still has to do its entire thing. So merge sort has to still divide the list in half. Has to still do its whole thing of dividing the list in half and getting it to its smallest element. 3, 4. And then it has to, sort and combine them. It has to check, which one's smaller. 1 is smaller than 2. And we know that 3 is smaller than 4. That was a bad 4. And then it, has to combine them again. Now it has to check, is 1 smaller than 3? Yes. Is 2 smaller than 3? Yes. And then we already know it's sorted. So there's some optimization, but it has to still do all of that thing. Well, bubble sort just is one and done, doesn't have to do anything. But as you can see, it doesn't matter what order merge sort's data is in. It's always going to take pretty much exactly the same amount of time. As you can see here. If it wants to look, there we go. As you can see here, and with my data again, it took for 2 million reversed, it took about 3.3 seconds. 2 million already sorted, 3.2 seconds, and 2 million random, 3.6 seconds. Those are all very similar tight timings. because it doesn't matter what order the data is in. It's going to do the same thing no matter what. There is slight variance, the sorted merge is on average faster than, reverse and random merge. I believe that's just to do with actually having to do less swaps, which is just going to be more efficient anyway. But still, it's microseconds. At most, the highest difference is 7 milliseconds. Who cares about 7 milliseconds really when comparing 2 million data points? So yeah, that's just why I believe there's a slight variance between each of the different random sorted reverse merges, despite them doing the exact same job on the exact same data set. Let's just do this quick. So yeah, and that's why merge sort is special. It doesn't assume that an array could already be sorted. That means, even an algorithm like bubble sort technically could be better. Merge sort is worst case optimized, and that means we're always going to have, super bad. That means no matter what, even if the data is the worst possible data we could ever get, it's still going to be the most optimal solution for that data when using a merge sort, right? It doesn't matter what order that data is in. Bubble sort, on the other hand, absolutely does compare about what order the data is in. As you saw, if it's already sorted, boom, automatically done. Don't have to worry about it at all. Faster than merge. But on average, and especially the worst case, it's going to take so much longer than a merge sort that, unless you're 100% sure that the data is pretty much already going to be sorted with maybe one number not sorted, bubble sort is awful and should never be used. Always use a divide and conquer algorithm like the quick sort we learned in class, or this merge sort. Yeah, thanks for listening. Have a good one.